we saw directional light. I mean, the light which has no position, it only has direction, like sunlight. I mean, sun never knows that who is placed where. So it just emits the light, it just throws the light. So when we do the lighting calculation for the directional light, we only see the direction. If I say Z is 1 and XY is 0, then it is from direction Z. Okay? Z is 1 or 10 or 100, 1000, doesn't matter. So that is directional light. We can rotate directional light. I mean, it is X0, Y0, Z1.1, and now it is X1.1, Y0, and Z1.1. X1.0, Y0, and Z1.0. So it turned the direction. It turned the direction, but still distance doesn't matter. From that direction, light is coming. So directional lighting we saw, movement of the lighting, that also we saw. Projection matrix, that in projection matrix orthogonal projection. So that we saw, and we saw the kind of a specular coloring. So specular reflection from the material point of view. So that we saw. What about positional light? A light has position rather than direction. Anyway, light will have a direction, but it has position also. How position matters? Like if I have a vertex, then earlier I was just, if I am considering the specular component at any vertex, like in kind of in fragment shader, fragment color is assigned per vertex. In per pixel, but it is decided like we set the kind of color at the vertices level only in the vertex shader. With that, with the vertices rasterization happen, and whatever the color at vertices and whatever the shading model is, fragment shader thinks about the fragmentation. So we decide the coloring at the vertices in the vertex shader. When we decide for the coloring in the positional light, so if I just talk about the specular one, then I have the normal vertex, normal normal vector. So I'm talking about each vertex. So when I am thinking about coloring each vertex, then normal from the vertex matters, and another vertex matter from vertex position to the light position. There is also one vector passes. That is the light vector. Light vector, earlier light vector was directional. It was coming in a direction. Doesn't matter where the vertex is. It is coming from. Like sun is a directional light source. It doesn't know where the vertex is. So it only comes in a direction. So when we are talking about the direction, then direction of the light means the kind of the light direction with the normal to the vertices, both we are doing the dot. Now normal from the vertex, okay, anyway it is there, and the line from the vertex to the light position, that line crosses, that is the light vertex, that is the light vector. So new light vector. Earlier light vector was decided. Now light vector could change the kind of orientation in rotation format, but now also it can change. But the actual line vector is wherever the actual light vector is wherever the light position is there. So from the vertex point, for each vertex, when we are talking about coloring at each vertex, from the vertex point to the light point, if I draw a vector, so that is the vector. So that vector and the vertex normal vector, that will do the dot, and then we'll decide of the kind of coloring at the vertex. So that we'll see. We'll see perspective projection. So perspective projection now it can sense the depth. We'll see ambience, we'll see specular, we'll see shiny. So we'll see positional light, we'll see perspective, and we'll see the rest of the component of the lighting. We talked light now. We talked about the specular reflection. Now we'll see other reflections like now we talked about diffuse reflection. So after diffuse, now we'll talk about the specular, shininess, ambience. Okay, so these three things that we'll consider. So if I talk about specular, a specular means shininess, diffuse means the coloring. So the shininess reflection. So it matters between two dots. Okay, the way we discussed. So it matters between two dots. One dot, vertex normal to the light vector. One dot, and another dot between I vector. Okay, I vector to the normal. So, or rather, I can say that it depends upon the I vector and the light reflection. So we'll see that. So computation is more. We are pointing towards two dots. One dot we have seen in diffusing. One more dot will come into the picture. So that we'll see. Okay, so we covered directional light and ortho projection. So we'll proceed for the projection type and the light source type. So light source type we have. So in light source type we focused on directional light. So next we'll focus on positional light. Okay, so positional light where light doesn't have any direction. So light matters where it is positioned. So that is positional light. Like if light is near to the model, then only nearby it illuminates. If it comes far from the model, then full model illuminates. Okay, so like if light is here, but still as per the distance, the area is illuminated, this area is not. So it is different from directional light. Okay, so directional light comes from infinite distance, whereas light position, positional light has a position. Okay, so position light has a position. So if I see this diagram, okay, so suppose that so this is L is light direction. The light from is a right now. So suppose that light is here. Okay. So light is here. If light is here, then light falls on the vertex. Vertex has normal. Then what about, so this point is we are calculating what would be color at this point. Okay, if light is parallel, then what about the color at this point? Still light will come in this direction if it is a directional light. If it is a directional light, light will come from this direction only. So light vector is not changing. Okay, normal would change. Here the normal is like this, and here probably normal would be like this. Okay, so when we calculate the diffuse, then this angle we are calculating. Now while calculating the diffuse, this angle will calculate. Okay, this angle. So this is directional light. But when we talk about the positional light, so light is positioned at that location only. So the light direction is this. And normal is, light direction is this. Okay, whereas normal light direction is this. Okay, so whereas normal is this. Okay, so it is different. Earlier light direction was this in parallel. So light direction changed now from this to this. So now what is the light direction now? So wherever it is positioned, the vertex where it is after model view matrix rotation, and wherever the light is, if I differentiate this, then this will give the direction of this vector. If I differentiate L minus the current, okay, so L minus the current position, so this will give the light normal. Okay, we don't need a kind of transpose and inverse or whatsoever. We are getting in this fashion only. So this is new light normal, new light vector. Okay, if it was a directional light, then light vector was this. Okay, now light vector is this. Surface normal will not change, but this angle we would have bothered this angle. We would have bothered this angle. Okay, now we will bother this angle. So this is the computation difference between the positional light and directional light. Okay, so this is directional light, this is positional light. Probably we can save it. Okay, so I can insert that. Okay, so this calculation that we will bother now. Okay, so L is changing. Okay, in diffuse calculation. So L is changing. N will be the way it is. Okay, so we'll use positional light and then perspective projection also we'll add to the code. So where we were, so we'll start from there. Okay, so this is the code. Now we'll modify this code. Okay, so vertex color will change now. So this is old vertex color. So new vertex color. So RGB dot normalize model views, but this won't change. Okay, this guy will change. What it will change, that will show. Okay, so model view light. Model view light. How much light is changing if I am rotating the light? So light position we are hard coding as 10. Probably I'll change it to 5 because I'll change the kind of perspective. So looking at its distance. Okay, so it is 5 now. So this is 5. This distance is 5. In Z direction. Okay. So model view light minus wick minus model view sphere into whatever the wick for how much coordinate has moved by then. Okay, so that's it. Okay, so now rather than going for fixed, here what we were doing was we had a fixed direction, this is directional light, and we were rotating the directional light through transfer because it's a normal, it's a normal surface kind of. It's not there are two kind of coordinate. One is on the surface coordinates. If I have a model on the surface of model, there are points, or if there is something that is normal. So if I want to translate, if I want to transpose, if I want to kind of doing transformation on the normal, then I have to go with transpose inverse. If I have to do transformation on the surface, any point on the surface, then we will go with the normal model view matrix without transpose and inverse. So suppose that this is the light, this is somewhere in the surface, there is nothing like normal. Then we will modify the new location like this. Okay, now it is 1 as we want the calculation to happen. So fourth parameter is the W parameter, and it gives importance, it comes into importance when we do matrix multiplication from the model view matrix. So it is 1, anyway it is 1 for the positional light in the fixed function pipeline, minus model view sphere into whatever coordinate it is moving. Okay, so it is called I coordinate. So this is called object coordinate. If I multiply by model view light, so this is the new transformed coordinate, it is called I coordinate. So this is another transform. So for the light position that I have made it fixed, this is the new transform position, and the whatever coordinate we are receiving, so coordinate means each coordinate, this vertex shader is getting called. So that much. Now we do the calculation and then XYZ and we normalize. That's it. And now we'll move to, so these are the codes that we have written. Now we'll move to reshape, and then probably it's time to go for GLU perspective, and we will make somewhere like okay, 0.5 is okay to 20, it will be big, or we'll leave it 10, then okay, fine, okay, we'll see. Okay, if required we'll do, and this translate we will do -5, so it will come in the middle. Earlier we were using 1 to 20, let's make it 1 to 20 so that it will be same as what we did. Okay, and we will translate it to -5, so we will make it same as -10, so it is going -10. Okay, light is at the 5, so it is 5 before the new origin. So new origin is shifted to -10, and whatever the new origin is, from there it is 5 in the z direction. That's it. Okay, so it will be shown. Okay, so we can try. Item 3. Okay, so there is no model view matrix, model view light, the way we stated. Okay, so we will comment this, and instead of that, now we have another matrix called model view light and transpose light. So transpose light here we had, so we will comment this and we will have model view light. Okay, now we have this. Okay, so light calculation, so we just comment this and now we have model view light. If it is that, then we don't need these calculations. Okay, pretty straightforward. Okay, now these attributes are also looks good, and now I can place it near. So I'll press. So light source is at 5 distance, so I have placed it will go near. Okay, it came near. So this will not happen in the directional light. Means either it cannot move directional light. It will change the direction in angular fashion, but it is at infinite distance. You cannot move sun. Okay, it will always be at infinite distance. But positional light we are moving, and light went inside the model. Okay, now light will come out. Okay, now so light is changing its position. Light can go right. Light went to right. Light can go left. Light went to left. Okay, so I can print the situation. So it is -1 and 0.6. So I'll press right, so it will come to kind of 0.6 still. Okay, idea is that, okay, so it went too much right. It's pretty well. Now I can rotate the light. Okay, so it is 160 degree. Light went behind. So now if I rotate the model, there won't be any light at all because light is backside. Okay, I'll change the light. Okay, what is its position? So light is at 200 degree. Oh, sorry, light was at 310, now 380. So light is kind of 360 degree to move. So light is at front. Okay, so this is the position light and perspective position. If it is a perspective position, then if I press far, it will go behind. So okay, so it should go behind. is going in that direction. Okay, so probably we will rotate little bit. Okay, so it is going behind. Now it is cutting the now I can bring in front. This is perfect, and it is going behind. It went out of the projection matrix. So this is the magic of okay, so why? So we'll do one thing. I mean, light is not pretty clear where we are pressing and where the light is going. So no one. So I think image is there. So we'll leave it. Oh, okay. So we'll have to cancel it. Okay. So now we'll add a kind of a light source so that it will be visible. Okay. To add a light source, we need to have a kind of another shader code. So we'll copy here. So frag shader, frag code, vertex code. So I'll say word code equal to till here word code equal to okay, so probably we'll copy paste 42 and 14. Okay, so 14 to 42. Okay, so it can. Okay, so now we are moving towards having another vertex shader so that we can show the light. So this is vertex shader 2. Now we have projection 2. Okay, so we have model view light. So that is 2. We have coordinate, that is 2. Okay, varying vertex color, so it is internal, doesn't matter. Now we have okay, so color is will make it 1, it will be completely white. GL position is projection 2 multiplied by light 2 and coordinate is 2. I can give code only, light only, doesn't matter, but it will be easy in remembering in the kind of init object the what we did, and that's it. And vertex color equal to color. So GL position is projection 2, model view light 2 and code 2. Okay, and fragment color is same, so fragment code is 2. Now we'll have a light source, okay, in white color. That is the idea. So this code will also duplicate up to here. $68, 85. Okay, so I'll say 68 to 85. Okay, now we have kind of another set. Okay, so this is all right. Vertex coder 2 and fragment code 2. Okay, and then shader program 2 and attach, so no problem, link to shader program 2, shader program 2. Okay, so GL use, so we will leave it here only. Okay, so probably we can remove this from here. Okay, so now we have shader 2 program and shader 2. Okay, so we will do it again for YY. So for this only I was setting as 2. Now it is projection 2, model view light 2. Okay, and we'll set attribute like this only. Here it will be in shader program 2 and here it will be in shader program 2. So it is called 2. Now we set this also. Okay, now we will have buffer of 2. Sorry, so here a mat. Okay, fine, no issues. Okay, so we'll have one more buffer. So VB01, VB02. So here one more have VB01. So idea is that in future we'll place this in some library code so that it will be easy to call. So pause buffer. Okay, so probably we'll do after we do everything. So we'll remove this for the time being. So let it be the way it was. And now vertex array 2 and it is 0. VA opt, and here we are letting it to 1, so that we'll see later. So this is the code for the VA of 0 and we are setting everything. So done. Now we'll copy this. So VB 0. Okay, so 1 pause array nice. Okay, and we will have another called mat2. So mat2. Okay, so we will, so here opt file is whaleshark.opt. Now we'll have kind of q.opt. Okay, and there will be q and bb gen buffer 1 pause buffer, and then we'll get mat2. Okay, now we'll copy this to YY. Now GL bind vertex array 1, and in that attribute pointer is called toLock. Okay, vertex attribute point init called toLock, and here it is pause buffer. Okay, so pause buffer we initialized and jail buffer data we pushed. You will see mat2 and 3 to 8 only vertices, and then we create GL bind vertex array 1 enable. Okay, okay, GL enable vertex lock 2 and then attribute pointer log2, and then okay, so this we don't need. GL buffer, pos buffer we have done. No. Probably it will come here. Okay, so GL enable vertex attribute array log, GL bind buffer, pos buffer, whatever we created. Okay, and GL vertex attribute pointer. Okay, so I think this looks well. Okay, so now here temporarily I'll say GL use. Okay, shader program. So GL use program shader program, and initially we'll set the lighting to 1. Okay, so lighting is not disabled. Now it's time to set these variables. Okay, so VA of is set, mat is set. So we'll set mat 2 now, because now we have 2 vertex and fragment shader. Okay, we'll set shader program, and we'll set shader program 2 so that we can use it later. Okay, and we'll have another attribute. We want to display the cube or no. So init cube. So initially we won't display the cube. Okay, we can place it here. It will be cleaner, I believe. Okay, now use shader program, and that's it. Okay, so probably we are done, and we'll come to display. So nothing need to be touched. So everything will move the way it is. Here we'll say GL use program init dot shader program. Okay, now everything is done. Now it's time to use another code that we have written for cube. Okay, so if init dot cube, if that is the case, then GL use program init dot shader program to GL push matrix. Okay, so we'll copy this and we'll proceed with the same translation for the light source, because it will move the way the light source is, and we'll position GL translate 005. This is what we did in 0. So light position is set as 0005. So same thing we are doing. Okay, now we'll copy projection here, and we'll copy mode lighting here. So projection will copy here. So projection code what we had done. Okay, probably I think it won't change, so we can copy it here only. Projection 2 and same projection, whereas this model view light, so this will copy init cube GL uniform matrix 4B and init model view light 2 lock, okay, and model view matrix. That's it. GL bind vertex array init.va opt 1 and GL draw array GL triangles, 0 len init mat 2 by 8. Okay, so now here we did binding for VA ops, so it will be 0 and VA op it will be 1. So we can do GL pop matrix. Okay, so now for the cube GL use shader program 2 push matrix, do the translation in for the light source, translate to 5 and then push model view light 2 lock and then just do the drawing. That's it. Now here in the keyboard, okay, so cube will set reset in the keyboard. So I think for the cube we can make CC. So if it is C, key decode, okay, so set attribute, okay, in the init for the cube it will be 1 if key equal to C is 0. Okay, so it is completely done. Okay, so no one stops us trying our luck. Python FGL light. Cube object is not there, so we'll copy. Temp image glow as cube object. We'll try again. Okay, invalid value code 2 is not there. Now we have word 2. Inside that we have attribute code 2. Okay, normal is not required. So attribute code 2 varying vertex and color and code 2. Fragment code 2. Now we have word shader again. Okay, and here we are shading word code 2, word shader, frag code 2, frag shader, and now shader program 2, GL attach shader program 2, link shader program 2. Okay, now here projection 2, model view light 2, shader program 2, we are getting attribute location for the code 2, we are getting the attribute location and setting in the init. Okay, so we'll try luck again. Oh, it is coming. Okay, now I'll press C and let's see if cube appears. Okay, I am pressing C, but cube is not appearing. Oh, appearing. Good. And it should vanish. Vanishing. Appearing. So, cube is appearing. Now, light source we can see where it is. So, I can rotate the light source. Okay. Now light source is visible. There it is. Okay. I can take light source left. Okay. I can take it right. Okay. Now this light source I'll make it go near to the object and it is diminishing, light source went inside. Okay, so light source would come now out. Okay. Okay, so there is nothing much informative. So we just did so that light, we don't know where the light is. So positional light, it really matters. Okay, so if it goes near to the model, then so this we cannot see in the directional light. Okay, so that is the phenomenon. Okay. Now full light. Okay, and I can rotate. Okay, so should appear bigger, and if I send it, it will keep appearing smaller and smaller. So this is perspective projection. Okay, so this is how it is. Okay, because we change this transformation axis, so we'll make it right. So it should be better. It is perfect. Okay, so we'll move to the next topic. Okay, ambience, diffuse and specular. So this is, if we see little closely, then there is a red spot. So this is specular, it's shining. We can move the red spot. Okay, because means light has moved, so red spot has moved. This what we are seeing at the back side, this is ambience. Okay, so no much engineering is required. Means shader programming is kind of means it takes care of many things. We just need to add it in shaders. That's it. Okay. Otherwise, in the fixed function pipelining, kind of we would have to do much more thing. Okay. Now we'll open this file. Okay, so we'll comment it again. We'll rename this color to kind of diffuse color. Okay, we'll make it 1. Okay, shining will come perfect. What else color we need to add? And here we'll make specular color. Specular color. Okay, so that is red, and a specular exponent equal to 10. So we are slowly moving towards the net light calculation. Okay. Here, whatever we have, the net surface normal in powers to the shininess. Specular light, specular material. So specular light we are not mentioning. Okay. So here I can mention whatsoever come to my mind. So diffuse is L dot N that we have seen. Now specular is L dot N plus E dot N. E dot N, this is N and this is E. Okay. Okay, so we'll write the code. Vec 3 NLRV. Okay, so we'll see what is NLRV. So V is E here. Okay, so probably I'll make it E. Okay, so normal is whatever we have calculated. Okay, so that is normalize model view. I think it's not a bad idea to copy paste. Means it is understandable what we are doing. So this only we will just copy paste. Normalize up to here. Because this is same. Okay. Then we have L equal to normalize and vec 5 minus, so it is same. So this for diffusive component N into L that we have anyway done here. Okay. Now we have E equal to this we are adding. Normalize. Okay. We are considering at 0, 0 position. Okay. So vec 3, 0, 0. Where is I? So I is considered at a fixed location. Okay. So I can say vec 3 0 0 minus, so I am considering I, it is, okay, I is pointing here, so I is in the transformation, I is at 0 0 0. This is kind of in projection matrix, this is what we consider for perspective projection. So vec 0 0 0, I mean, it can be changed, like I is here somewhere, I can change it. Where is my I? So I am considering at 0 0 0. Okay. So that would come to model view sphere into vec4. So I would move chord 1.0. Okay, so I position to the wherever is my coordinate dot x, y, z. Okay, so here light position wherever I am drawing it, and here I position and wherever I am drawing it. So this vector. Okay, so this will become a net vector as I vector. So vector 0, 0, 0 minus model view sphere. Okay, and a vec4 coordinate. Okay, now we'll do the computation. If dot L dot n less than equal to 0.0 means it is backside. Okay, if that is the case, then vertex color equal to, okay, so this is ambience 0.5 and 1. Okay, 0.05, so it is 2 less blue. Else, okay, so probably we are inside something, so we will choose. Okay, else vec3 color equal to 0.8 into dot L dot n into diffuse color dot RGB. If dot R, okay, so now we are calculating the second part. L dot n we did and E dot n that we are doing. So E is E, okay, so L dot E so L dot E into diffuse color dot RGB. Okay, so we are in if statement. So if dot L dot E vec3 color if dot R dot E greater than 0, color plus equal to 0.4 into power dot, okay, so L dot E specular exponent into specular color dot R. Okay, now vertex color equal to vec4 color, okay, diffuse color dot A. Okay, so finally we are done. It was little complex. Okay, now we have NLR. So R we are not calculating. There is something R. So I'll just leave it. So N, L and E, the way we promised. So N and L anyway it is called calculated. E is from 0, 0, that is the I position, minus model view sphere, the where the coordinate is rotating. So that we normalize. Okay, if L dot N is less than 0, means we are at kind of wrong side. In that case, only show the ambience. Okay. Else we have a color. So for diffuse 0.8 dot L dot N and diffuse color dot RGB. Now we are in another business, E dot N. So L dot so N dot E. Okay, E dot N or N dot E. So dot N dot E greater than 0, then color plus equal to power dot N dot E into a specular exponent, that is 10, and a specular color dot RGB, and vertex color equal to color. Okay, so we have set exponent as 10. So I believe we are done. Okay, so we have done all the calculation the way we said. Okay, it is both we have to add, and then so we are not adding straightforward. It is because it is 0.8 and it is 0.4 and power. So this is the actual calculation. Okay, so N dot E. This is okay. So we'll try specular component, specular color, diffuse color. Okay, so there is error. L less than equal to 0, less than equal to 0, then vertex color equal to. Okay, so normalize. Sphere into dot XYZ. This is perfect. Okay, so model view sphere, whatever come XYZ, and then decrement it, and then do the, or we can just remove it for time being, just minus. Okay. Okay, so okay, so dot take comma. So try again. Color undeclared. Okay, so here it is diffuse color. Okay, so at the beginning only we got the result. So we can see kind of okay, so shining is there. Red color shining, this is what we wanted. So I shall press the Q. Okay, so this is what we were looking for. So this is red color shining. Probably this will be more clear if we use the sphere. So here I'll change it to sphere. It's there. Okay, so red color spot can be seen. Okay, now I can rotate the light. Okay, one demerit is there. The shining part, it is not rotating the way we want. Okay, so that is the problem we are seeing. Otherwise it is okay, all right. Okay, so we'll change this to kind of okay, so we'll introduce a new thing that is called reflection. Okay, so we'll use now, there is something called reflection, and this is R. Now, reflection, if light is moving, then reflection would also move. Okay, otherwise, normal. Okay, so the way, otherwise it's fine, means whatever we are doing the calculation, it's okay. But if light is moving, we are not able to use it correctly. So we'll use another guy called reflection. So we'll have now R. Okay, now reflection will have its own calculation. There is a ready-made built function reflect. Okay, so light to the normal, we will use reflection, and this N will be replaced by R, and this N will be replaced by R. So now we'll try again. So Ln for diffuse color, whereas R and E for a specular color. So we'll try again. Okay. Now we'll rotate the light. So I'll bring the light cube and we'll rotate the light. It is rotating. Since light is rotating, its reflection is rotating, we change the vector. Okay. Now I can change the color of the specular. So specular color is red. Okay, let it, and diffuse color will change, so we'll make it green the way it is. Okay, so diffuse color change, and red is not very prominent. Okay, so this is how it is. So sphere can move up Okay, so light is shining is going down because it is moving up. Shining went to right side. Okay. I can rotate the light. Okay, so clearly it is shining. Shining color we can change. So shining color is red. We'll make it kind of this color. Okay, it is prominent. Looks like white. Okay, so if I keep it as diffuse color as white only and this color as red, and we'll bring back our shark, Mr. Shark. Okay. I'll make GL clear color as black only. Now we'll rotate this. We're rotating the light, whereas I want this. This is blue. Okay, so probably I'll rotate the light. This is blue. This is ambience. I mean, I can make it even prominent. Okay, so probably I'll make it 0.9, 0.8. It will be prominent. Okay, now I'll rotate the light. This is blue. This is not black. I mean, I can make it more prominent. So probably I'll make it 0.2. And light comes. This is okay. So this is ambience. If light is not there, still we can see the color. Okay, so this is ambience. If light comes in, now we can clearly see the ambience, and if light comes in, then we can see the red color shining. So that is the specular. Okay. So as per the lab exercise, so in Earth we can see the backside as ambience. So I'll bring that. And here, as per the exercise, it is black. The diffuse color is green. Okay, so I have light and I'll rotate the light. This is This is ambience, the blue color. And right is rotating, and we can see the shininess, and so green color is specular, so this is ambience. Green color is specular, and what red shininess, that is we are seeing the green color is diffuse and red color is specular. Okay, this is perspective projection, so okay, this is how it is.